Solar flares are powerful bursts of radiation and energy emitted from the sun's surface, showcasing the dynamic and energetic nature of our closest star. These explosive events are driven by complex magnetic interactions within the sun's atmosphere, offering insights into solar physics, space weather, and their impacts on Earth and space-based technologies. The science behind solar flares encompasses solar astrophysics, plasma physics, and magnetohydrodynamics, unraveling the mechanisms that trigger and shape these intense phenomena. Solar flares originate in the sun's outermost layer, the solar corona, which is a region of extremely hot plasma, ionized gas, heated to millions of degrees Celsius. The corona is threaded with magnetic field lines that extend from the sun's surface into space. These magnetic fields can become twisted and stressed over time due to the sun's differential rotation. The equator rotates faster than the poles, and convective motions within the solar interior. The primary trigger for solar flares is the sudden release of magnetic energy stored in these stressed magnetic fields. When the magnetic field lines reconnect and realign, a process known as magnetic reconnection occurs. This rapid reconfiguration of magnetic fields releases enormous amounts of energy into the solar corona, heating plasma to temperatures exceeding tens of millions of degrees Celsius. The release of energy during magnetic reconnection accelerates charged particles, such as electrons and protons, to near relativistic speeds. These energetic particles stream outward from the sun along the newly formed magnetic field lines, generating bursts of electromagnetic radiation across a wide range of wavelengths, from radio waves to X-rays and gamma rays. The intensity and duration of solar flares can vary widely, ranging from minutes to several hours. Solar flares are classified into different categories based on their X-ray brightness, with the most powerful flares classified as X-class flares. They can also be associated with coronal mass ejections, CMEs, which are massive expulsions of plasma and magnetic fields into space. CMEs can travel at speeds of millions of kilometers per hour and, if directed toward Earth, can interact with Earth's magnetosphere, potentially causing geomagnetic storms and disrupting satellite operations and communication systems. Scientists study solar flares using ground-based observatories, space-based telescopes, and spacecraft such as NASA's Solar Dynamics Observatory, SDO, and the European Space Agency's Solar Orbiter. These instruments monitor solar activity, measure radiation emissions, and capture high-resolution images of solar flares to better understand their physics and predict their impacts on space weather. Understanding solar flares is crucial for space weather forecasting and mitigating their potential impacts on Earth and space-based technologies. Space weather forecasting involves monitoring solar activity, predicting the likelihood and intensity of solar flares and CMEs, and issuing alerts to protect astronauts, satellites, and electrical infrastructure from potential damage. In summary, the science behind solar flares involves the complex interplay of magnetic fields, plasma dynamics, and energy release mechanisms within the sun's atmosphere. Through observational studies, theoretical modeling, and technological advancements, scientists continue to unravel the mysteries of solar flares, advancing our understanding of solar physics and enhancing our ability to predict and mitigate their effects on Earth and space environments.